Okay, we can start. So this is about mounting object stores in HDFS and how we can accomplish that by using the storage tiering feature. Yeah. So we're at Western Digital. You will come clear like Western Digital, Hadoop. What's the story? That will come clear later in the talk. So we're in the data center systems division in the engineering. So I'm Thomas. I'm the engineering owner for all the object storage data pod stuff. So we have an object store. It's Amazon S3 compatible. So it's a customer-facing data pod features and also Hadoop integration. So that's actually where I started off in. I joined in 2014, and I started off on the Hadoop integration. That's just when the Hadoop file system S3A got introduced. At least the Jira got started. And so then it got released in Hadoop 2.6, and then Hadoop 2.7, Hadoop 2.8, Hadoop 2.9. Things keep getting better and better and better. The object store optimizations, so we had small things in the beginning, like making sure you can use other endpoints, etc., etc. Instead of writing to local disk, write from memory directly. And then there's a big one coming up, and so there's a talk directly after this by Steve Loughran from Hortonworks. He's one of the main guys driving S3A. So it's very interesting. You should go see it. There's finally we've cracked the rename problem on S3. But so today's talk is about something else. It's something complementary. It's about provided storage as an HDFS storage tier. And so before 2014, I was doing computer science PhD in queuing theory in Ghent.
Hi, I'm Ewan. I'm also at Western Digital, of course. I've got a few HDFS contributions under my belt, including protocol level changes between the clients and the name node and data node. And I'm also working on this provided storage project. And I've also worked on quite a few different open source software projects in the past, HDFS, Hue, or Hui. Anything on Demand was a project I used to work on. You might have seen my name come up if you do a search for Spark TerraSort. Also, I'm a co-organizer of FOSDEM HPC dev room.
To go that way.
All right.
So everything we're going to present here today is done in open source around 9806. It's a ticket created probably about a year ago by Chris Douglas from Microsoft. Who's also in Hadoop PMC. At that time, we are like having the same thoughts, trying to figure out cracking the same problem. We saw the design doc. They presented at last, Chris and Virajit from Microsoft presented at last year's San Jose event, Hadoop Summit San Jose. We read the design doc, talked to them, and we exactly had the same goals. So let's build this provided storage tier for mounting object stores, Azure, or of course an S3 compatible system. We have the same goal. So link tickets, design doc. If you want to help out, it's there. I think also people from Intel have contributed some patches. So data in Hadoop. So why has Hadoop become successful? You put all your data in one place, and then you have common form. In the common format, you have common abstractions, common tools to process your data, to analyze your data. And so there are multiple layers, and so these abstractions at these layers are very powerful. Like for instance, at the bottom layer, the file system layer, you have the file system abstraction, and you have different implementations, HDFS, S3, WASB. Same holds for the layers above. If you want to do yarn, you can do yarn. If you want to do something else, you can do something else. Your application can choose you. Your scheduler you can choose. Your file system you can choose. Of course, HDFS is the well-established file system out of these. I think the other ones are younger, less mature. And so HDFS has a lot of nice features around multi-tenancy and like management APIs, how the admin can control the file system, around authorization, authentication, quotas, encryption. And it also has a very nice storage tiering and policy feature, where you have different storage tiers. You can set this directory, it's hold, it's hot, it's cold, warm, and that translates into what type of media this is stored into. It's going to be crucial for the implementation of our goal. So multiple Hadoop clusters, how can you manage them today, and especially how can you manage data movement between them? So in the first place, why do you even have multiple clusters? I mean, the name note as a scaling bottleneck. If you were at Sanjay's talk earlier, they're doing a lot of work to address that. There's also previous work, like around HDFS Federation, around ViewFS, and so everything that follows is completely compatible with those changes. Also the envisioned ones, and they reinforce the story actually. So there's another reason to have multiple clusters. You have staging, testing, production. You want to separate them, or there are some compliance rules or security. And so how can you move data between clusters? So either you can use the compute cluster itself to copy it. Typically, the DistCP application, you spin it up on 10 nodes. It moves data from cluster A. So you read from cluster A. The DistCP here is the blue box. You move it to cluster B, and then the application, the red A, can read and write locally. So why should you do that? You have big advantage. You have local read and write for the application. But of course, you use compute resources to do the copy. So it requires capacity planning in your cluster. You can resolve it inside the application. That's another part. You say, hey, my application. It can contact cluster A and cluster B. And in the client, we will resolve all this. Of course, every time you add a new application, it needs to do this. It needs to keep the consistency. The applications itself also need to be consistent between each other, so it becomes quite a mess after a while. And you need to authorize independently. There are no opportunities for sharing a lot. So it's also, this approach also has its problems. It can work for use case, but it certainly is not a solution for everyone. So our proposal is actually to build this into the platform itself. So build this into HDFS itself. It's actually what we want to accomplish. It's simply a mount. And so it's a very well-known kind of abstraction. So you want to mount a remote namespace and synchronize storage in that way. So what does that give you? It's transparent to users, so users don't actually know that namespace A here is mounted underneath namespace B. Users don't need to know. The admin can manage that. There's opportunities for caching or prefetching. There's opportunities for sharing. And you present a unified namespace. The downside, of course, is that conflicts may not be automatically mergeable. If you update in B, cluster B, you update the mounted part, and at the same time you have direct writes to the mount itself, then some conflicts may arise, and then either you need a policy like this one always wins, or you need to do some Dropbox thing where you rename stuff to some temporary file, and you push it up to the user, like resolve this conflict. So we want to mount Hadoop-compatible file systems that provide a storage system inside each other. So you want inside HDFS. You want to mount another HDFS cluster, or of course an object store. We're here today for our main objective is object store. S3A, the guys at Microsoft, of course, care about WASB more, but it works for all of them. There's nothing that prevents you from writing your own. And so what are the goals? So what do you want to accomplish? You want to do this without explicitly copying all the data. So if you mount something, you don't want to pull in all the data if it's not required. You want to present a uniform namespace. You want to allow multi-protocol access, so you don't want to, if you write something in the top cluster, in the mounted part, that in the bottom cluster they show up as like HDFS blocks without meaning. They need to keep the file or file object semantic intact. So you need to be able to write it through HDFS to for instance, if the bottom storage would be S3A or an S3 system, you want to write it there, and then if the top cluster you unmount, and you can read the data back with any S3 client. That's the goal. Of course, you want to do this without affecting HDFS performance, or features like quota, security, rebalancing. If we could keep all those, that's really a goal. We want to keep all that intact. So evolution through the cloud, this is really a slide that Hortonworks, I think Chris Norad presented this last year, a slide of the evolution of Hadoop and the cloud. So how have they been interacting? In the beginning, you just had backup and restore. So you have your HDFS, you take snapshots, you maybe can back them up in the cloud. Then eventually, people move to reading from cloud storage, still writing the output to HDFS.
Take a show of hands.
And then the third approach was like, because of like, for instance, for S3A, the S3A connector has improved a lot. This evolution has been made possible. I think a lot of contributions from Steve Loughran, Chris, also some guys from Cloudera. So here at the end, you really have input and output directly using S3A to the cloud, and you can still use HDFS for some temporary data or for some like latency critical real-time data. So maybe quick show of hands, has anyone like interacted with the cloud, like their Hadoop cluster talking to the cloud? Any? Yes, about 10, 15 people, so it's not too bad. So I think we want to present, so this can work perfectly fine if your application can talk to different storage systems. So you talk to the cloud storage, you talk to HDFS. If your application can manage that, it's a perfect model. But if you take it one step further and use this provided store, I think you have opportunities for writing through from HDFS to the cloud store, and also very interesting opportunities for loading on demand. So only when you access the data, it's actually loaded, or we envision even in the future that data could be preloaded, even depending on the scheduler or depending on the application. You can actually get the data into another higher storage tier in HDFS, and then only start the application when the data is there in HDFS itself. So some use cases, how could you use this? You could use the cloud simply as an archive tier. There's currently an archive tier in Hadoop where you run HDFS only, you don't run any compute there. There are new features in Hadoop 3 which make this interesting, like erasure coding would be very interesting in that regard, also having a cold tier. This allows you to have an external cold tier in a cloud store. And so that's a bit where we come in. So you can mount one bucket, mount multiple buckets in our proposal. And that's a bit why we're here today. So we're actually from a Belgian object storage startup, Amplidata, and we got acquired by Western Digital in 2015. They want to really move up from the device. They're a devices company by heart, but they want to move up the stack. So we were a software-only company, and now we integrate to this full solution. So it's a scale-out object storage system for private cloud, and if you want to public cloud, if you want to host your own public cloud, you can simply expose it to the world, and you have your public cloud. So the key features are of course, the Amazon compatibility, with small difference that we are strong consistent, so no eventual consistency problems. Of course, there's erasure encoding for efficient storage, and it's an object store, so scalability is linear. This is the big system, so it's 588 10 terabyte drives, which gives you, with the erasure coding overhead, about 4.5 peta usable, and it can hold about 5 billion objects. That's the other limit. And then we also have a smaller system, an entry-level model. So of course, this naturally can play the role of this cloud tier, where you. So when we were talking to customers, like they have archival storage needs in their Hadoop cluster, but of course the system is quite big, so they were quite established large players, and so because they have a large footprint, they also have a large investment in HDFS. And so when we were talking about this, you can do direct connection to the cloud using S3A. They said, like, but yeah, we have all this investment in HDFS, our admins know it, we have all these tools, and our applications are written for it, so we don't want to rewrite our applications. And so the other model perfectly works if you want to change, but if you are really tied into HDFS, for us, provided storage is a way to offer you the best of both worlds. You have your familiar HDFS abstractions, you have data locality for your hot data you keep in HDFS, and you have scale-out object storage to which you can push out your cold data. Second use case is ephemeral Hadoop clusters. Think HD Insights or EMR, or if you run your own Mesos Kubernetes cluster, your Hadoop clusters or ephemeral, which means that they go away. So you run your application, and then afterwards you want to tear down the cluster. You bring the cluster up, you load in your data, you run your application, you write your data back to the cloud, and then you can tear down the cluster once that's finished. So that's maybe a bit more modern. So there's a third use case. I'll be very brief on this in the interest of time, where there's these interesting papers about co-locating analytics clusters with latency-sensitive applications, because utilization, papers by Microsoft and Google, where it's only like 20%, and they simply kill off large parts of the Hadoop cluster for analytics. They lose suddenly you lose 1,000 nodes. And so by using provided storage, these clusters could, when losing 1,000 nodes, you're no longer in trouble. You need to start replicating all across the place. You know that this data is also safely backed up in the provided store. So when you have provided store as one of your storage types, you know you can always get the data back, and it's stored there in a highly durable way in the cloud, be it private cloud or public cloud. So what are the challenges in implementing provided storage? So you want to synchronize the metadata without copying all the data. So you want to dynamically page in blocks on demand or preload them by defining policies for prefetching or unevicting local replicas. You want to have a way to mirror changes in the remote namespace. So over time, you would like, if something in the cloud store changes, you would like to see this reflected in the HDFS view where it's mounted, and the other way around. Of course, writes back to the provided store need to make sense. And then the holy grail is dynamic mounting. Like you mount something, you unmount it, you remount it, detecting that, doing that in an efficient way, and then even mounting something in multiple name nodes, mounting a bucket, so in multiple clusters. Those are the big challenges, and I think that's about what we're going to do. And I think Hadoop, Ewan is going to talk about how we're going to achieve that.
So I'm going to talk about first the big picture, and I'm going to go into a lot of technical details. So I have sympathy that it's after 5 o'clock and you've had a long day, but he's explained the why we're doing this, and I'm going to get into the how. We've got 3 stages: the read path, the write path, and then we've got dynamic mounting. And today we're going to be talking about the read path. There's a proof of concept that exists, and this is basically how the proof of concept works. And we're currently trying to get this proof of concept into the HDFS 9806 branch. So to begin, the big picture, of course, is to start with an object store or an external store. So for instance here, we might want to mount prefix D, and we want to put that into the name node and have that mounted. This is so that you take a client, and the client is going to ask the HDFS system for data in D, E, without the C prefix, which is where the name node here has received this mount. It translates this to a call into the external store, and then that will, of course, return the file data back to the client. So at this point, it should be, this is a very high-level view. I hope this makes sense. But to review, let's talk about how we actually get data from HDFS in the normal vanilla case. So this, if you're a user of HDFS, maybe you're not too familiar with it, but if you program around it, then you might already know this stuff. So in order to get some data out of HDFS, what first happens is the client has to ask the name node for the block locations of a particular file. So in this case, we've got the client asking for DFZ1, starting at offset 0 and then some length L. And then this will return the located blocks, and then the client will return the information saying that you can find all of these blocks on data node 2. And then the client goes and sends the read block request to the data node, which will then, of course, return that data. So this is the basic way that HDFS currently works. The replicas are stored in the data node, and all the block information is stored in the name node. And the replicas don't really have any concept of what the inodes are. So what we're going to do, one bit that I need to mention, of course, is down here in the corner, we've got the different storage tiers. So within HDFS, you've got the different storage tiers. So you've got RAM, SSD, and disk. And so, for instance, in a data node, you might have your RAM here, your SSDs, and your disk. And what we intend to do is introduce a new storage type, which is going to be provided here, the purple prism. And this is going to be just like the RAM, SSD, and disk, but it's going to map to our external blocks. So again, we have our name node, which will map to the files to the list of blocks, which is how the client receives information about those blocks. And those blocks map to the various storage types and storage IDs, which would be the disk or the SSDs. We will introduce this concept of the provided storage, which maps the file to an inode, which maps to, again, to blocks, except instead of the blocks just mapping to the storages, they're going to map to block aliases. And these block aliases will have the appropriate information on how to receive this data from the external storage system. One thing that's really important to note here, so for instance, the block alias will contain the file URI, the offset, and the length, and then some information about the file, the contents itself, so that the data doesn't get out of date. So for instance, there's an out-of-bound change to the external storage system, someone does S3 put, changes the data. You don't want the HDFS system to, for instance, return half the blocks with some data and then half the blocks with the other version of the data. So this is to make sure that you get some semblance of consistency. So for instance, in S3, we would be using the E tag for the nonce, and then we would use the bucket and the file path, and then you use an offset and a length. Now what's important to understand about this is, well, a nice detail that comes out of this is that we're actually using the file-to-file mapping. So we're not just mapping blocks on the external storage. So for instance, if you use some sort of file system gateway or other tiering system, a lot of them will just say, yes, I can go get you block 1, 2, 3, 4, 5 on the external storage, and it will write a file on the external storage called 1, 2, 3, 4, 5. And if you come along with a new HDFS system, it doesn't map to the same blocks. No other person or anyone can use this because nobody knows what these block numbers mean. But in this case, you can still use your external storage. So we think that's an important feature that other systems that have done a similar tiering system haven't really done. Where are these block aliases going to live? We're going to have an optionally external storage called the block map. And the block map is a key value store, which is accessible by the name node and all the, previous in the POC by all the data nodes, but I think we removed this requirement by putting the information in the protocol. And the key value store can be an external service. So for instance, Microsoft is using the Azure table for this, which is an always available system. But if you have your own deployment, that's like yet another moving part, and maybe you don't need yet another service running. So what we plan to do is have this like a plug-in system, and you could use, for instance, LevelDB within the name node to manage these mappings to reduce the complexity and help people begin to use it. And then if you scale up, then yeah, you could use an external key value service. And then, of course, at the end, the provided volume maps to the provided storage type here. So the proof of concept works as an immutable cloud with an immutable cloud storage system. So here's an example running through how it works. So for instance, again, if we have from our overview slide, you want to map D into your name node, what we would do is we would first run a script which will generate the mappings for you, which will result in the FS image, which is what the name node uses to load up the paths and inodes from disk, and then also the block map. which will have all of the references and explain to the name node how to, or to the data nodes how to retrieve that information from the external storage system. So here the file system is mapping the paths to the blocks, and the blocks will be mapped to the provided storage system, and then of course the block maps will have the block aliases there. So how does this look in a diagram? Well, so the name node will have the subtree here, and the block map is loaded up by the name node. And the name node starts up with the FS image, as I explained, and then all of the blocks will be reachable from the name node. When the data node loads up, and it says, I am a data node with provided storage. Now, one of the issues that we need to work through is if you have something like 5 billion objects in your provided storage system, if the data node loads up and says, yes, I have access to this provided storage system, and here's all of the blocks that I can offer you to the name node, that comes up in the block report in current HDFS. And we envision that would be a huge problem, because if all the data nodes come up with 5 billion blocks individually, then that's going to smash the name node to bits. So we need to change the way that the heartbeats work. These blocks won't show up in the block report, and instead there's going to be work in HDFS 5318 to make these blocks shared in some sense with the other data nodes. Sorry?
So it's in contrast to 53818.
Oh, I'm sorry, in contrast to 5318.
So I think here what Sanjay talked about earlier about having like part of the namespace in the name node hot and part on disk also ties in really well with this idea of having a large store, and you want to mount as much of it as needed. So currently that's a small part of it. If the name node can handle more files, you can start mounting larger parts of it.
Yeah.
So
how does this look in contrast to how HDFS works at the moment with normal files mounted into HDFS? Well, for the client, it's just about the same. So the client asks the name node where to get files, or sorry, to get the blocks for this path. The name node will then will look up in the block map, which, as I said, could be within the name node itself, but it could be an external service, and it will see that, for instance, DFZ1 will be in provided storage, so it needs to ask the block map, and the block map will tell the name node that, oh, that's in the external storage in this location, which is then returned within the located blocks information, which is returned to the client. And it also says that you can access the data node 2 in order to get these provided storage blocks. That information is then passed through to the data node 2, of course, which then, well, I think this must be an older slide. It does not need to ask it uses the alias, which is the information here, to figure out where to look in the external store, asks the external store, and then returns the data. Yeah. Are there any questions? I think this might be a good point to ask for a question, because this is the complicated part. So, yeah.
Yeah, about the block reporting.
Yeah.
So why don't you just store the mapping of the blocks to the F3 locations persistently? Then you don't need to worry about big block reports going up. I mean, HFS doesn't do it because they want to reduce the amount of memory.
Yeah.
But we do it in HopsFS because we don't have that problem. And in your case, if you're going to store it in an external store, which I think is anyway a very dangerous idea because you're not going to do transactions across it, I guess. Why don't you just store it there as well?
So the question is why? Sorry, can I need to because you don't have a microphone. I need to repeat it. So can you?
Yeah. So to compress it, why don't you store the mapping of blocks to S3 locations persistently, so you don't need to have a full
Yes.
block report?
So why don't we persist the block map persistently as a key value store. So for instance, within the name node, you could do that. You could, if it's, for instance, using level DB, that would be persistent. But on when you are if you start up a new external store mount, a provided storage mount, you need to generate this key value store. Indeed, that would be in a persistent way, and then that's just loaded up. The name node is not going to start out scanning the external storage system, if that answers your question a bit.
You need to do in HDFS. You need to do a full block report when the data node starts. You need to do a full block report to generate the mapping of block IDs to host names. Right? If you didn't have to supply it, if you persisted that, then you wouldn't need the full block report when you start up. If you persist in an FS image, or if in your case in your block map,
I think that's exactly what we're doing, if I understand correctly what your question is.
Yeah, so it would map to a storage ID. The provided system is a storage ID, and they would say they're going to report that they have access to storage ID 1, 2, 3, 4, 5, and all the blocks therein are accessible. And that would be the change. That would be the change obviously I didn't explain well enough here, but that's basically the change, is to say, yes, I have access to this provided storage system, and therefore I have access to all of those blocks, and that's basically it.
That's exactly how it works.
Yeah.
Does all data nodes work as gateways?
I'm sorry?
Just all data nodes work as gateway, or do all?
That's up to you, I guess. So
repeat the question.
Yeah. So do all the data nodes work as gateways, or so that's up to you. It's simply a provided. It's a storage tier. So just like you can bring up HDD or SSD, or you can bring up your name node with provided, and then it works as a gateway.
Part of the data node configuration will be to say, does this have access to provided storage? And that's part of the DFS data node.ders. So currently you can say this has this disk in this path. There has been a ticket to change that into URIs, or optionally URIs, and then you can use those. You can say provided bracket, a URI to the provided storage system, and it says that it has access to that provided storage system. Yeah, so that's configurable on a data node by data node basis. So what are the benefits of this design? So one of the nice things is that, so for instance, in contrast to ViewFS, this means that the administrators can enforce quotas and limits on the storage tiers, because all of the configuration is done on the server side as opposed to in the client. And so we think that this also has a simpler implementation, because all of the various upgrades and rollouts can be done by the administrators. You can also support the various different backends for storage. So for instance, as Thomas had mentioned, you can use WASB or S3A. We plan also that you could mount HDFS within HDFS. Sorry?
Yeah, that's one of the must-haves.
Yeah, that's one of the must-haves. And the credentials are also hidden from the client, which means that if you want to use the HDFS to manage who has which ACLs, then you can use that to prevent people from writing, even though the data node has all of the access to do the puts. And of course, this enables us to do a lot of policies to improve the performance. So for instance, prefetching, doing read-through, caching, and there's research being done, I believe, at Microsoft to investigate how to prefetch things efficiently so that the data is already available. So one of the main issues, of course, is that there might be out-of-bound changes. So out-of-bound changes is when you have your S3 storage, for instance, your object storage, and someone else is using it, and they start adding data to it, and then the HDFS needs to be updated in order to know what these new objects are, what's changed, and so on. I'm sorry?
Especially overwrites.
Yeah, especially overwrites. So when someone's written over your data, you'll need to make sure that the nonce matches. And so there's basically two ways to approach this sort of thing. One is to asynchronously just poll the data and try to keep it up to date as best you can. But then where available, we think much better way to do this is to do some sort of shared log system. So for instance, if you have access to the transaction log of your object store, you could continuously get the updates that way, and you don't need to poll, and hopefully the eventual consistencies don't cut your fingers off.
To make it a bit more concrete, a second example would be like Amazon has Lambda, where you get callbacks on your changes to your S3 files. You could use that to update the mapping.
Yeah. But of course, I'm sure if you were aggressively trying to find corner cases where it doesn't work, I mean, we're gluing two very large, complicated systems together, and of course there's going to be ways that work that won't be very efficient, and you'll end up not very happy. So we're trying to be open about where this is good. And this is basically, we think, where people are ingesting data into one bucket, they do some ETL, and then return the results into a different bucket, and then those are used by various analytics. If you start reading and writing from the same bucket, you're going to get all these sort of collisions and conflicts with the nonce, because any time that it's out of date, the mapping is out of date, then you're going to run into unhappy days. So if the data is going in one particular flow and out the other way, then we think that that would be actually the sweet spot for this sort of for this system. And so the implementation roadmap is, I've explained the read-only sense. What we're trying to work on at the moment is the write-through and write-back. So for instance, with write-through, that would be useful for when you're using this as cloud backup. But one of the issues there is when you've got a very busy write, and the object store is very busy, and the name node is locking and trying to write multiple things at once, and the latency will increase because the lock won't be released until one of the files has been written through to the object store. So write through is when you write to HDFS, but it's not going to return to the client until it's actually been written to the object store. So in that case, it introduces the latency of actually writing to the object store and getting that in there, and then returning back to HDFS that it was complete, and then returning to the client. So that introduces the latency. Then there's also write back, which would be lazily replicating. So you write it to the HDFS, and then that will replicate it as it goes, which would be a good choice for some people. But then the thing that we think is the best, well, what we're most interested in, and we think is the biggest challenge, is dynamic mounting. So from an administrator's point of view, if you have an existing HDFS cluster, it's not ephemeral at all, and you want to use this, you've done a rolling upgrade to a version that has it, you need to get one of these provided storage systems in, so you need to mount it, and that's actually really quite complicated, so that's something that we're currently architecting at the moment as well. So if you want to get involved, these three are some really good places that are still open for active design, architecture, and implementation. And we're going to be talking again in San Jose. I think it's Thomas and Chris Douglas presenting? Virajit.
Yeah.
Virajit at Microsoft. They'll be presenting work about the right path, which the right path we think we have most of, but there's still time to get involved in that if you really want to help guide it to your particular use case as well.
So this is really, Chris Douglas presented this last year as an idea, can we make it work? We implemented the read path. We're fairly confident that this is a good way to do it, and it works efficiently, and so now we want to present our ideas on the right path and dynamic mounting and get feedback from the community on those. So here are the resources. The ticket is HDFS 9806. There's a lot of subtasks that are available for work. We had someone from Intel, Jiajia, I hope I haven't mispronounced it, Jiajia Li in Shanghai. She's submitted a patch, and yeah, there's currently, otherwise it's been mostly a joint work between Microsoft and Western Digital. But yeah, we're very happy to get more people involved. And yeah, if you have any questions, we'd be happy to discuss everything. And if we run out of time for questions, we're around the conference, and we're pretty nerdy people, so we're happy to talk about this all night. With beer.
Yeah. So, are there any questions? Yes.
Some of the things you mentioned were around write consistency.
Mm.
Is there any overlap there with what is, I think it's the S3A Uber 3 that Steve and a few others are working on, where they're looking at having some consistency store behind that. Amazon already do that with S3, their proprietary S3 driver. They have an option to use Dynamo or something behind the scenes. Is there overlap there, or is that specifically where you're saying to use level DB?
No, so that would completely tie into this. So what would happen there is once you the data node actually uses S3A to do the data transfer. And so if S3A would improve there, so that is completely to get around the eventual consistency problems with Amazon. I think Amazon pulled in the thing about Netflix, and now Steve and
Amazon replicated what Netflix did.
and now Steve and co are replicating that so that will be a better S3A connector. Then you will also get full consistency guarantees against Amazon. For our system, we already have it built in.
And for people listening, I think that project is S3 Guard.
Yeah.
So if people need to Google that or DuckDuckGo
Yeah,
that, they can look up.
Yeah.
Yep.
So also interesting stuff.
Yeah, Steve's, the next sessions after we're done with questions, he has a talk on
Yeah.
S3.
Yep.
With Sanjay, another room. Yeah, just in 10 minutes, I guess.
Yep.
We have-
Yeah. Any other questions? Yes.
People are talking about containers for storage for HDFS for the future.
Mm-hmm.
How do you see that in the context of containers for HDFS?
So the question is, how do we see? So people are talking about containers for HDFS, and how does this work with the containers? I think they're orthogonal because the containers are to collect the blocks together, and I've been monitoring it to see if that there's any conflicts of interest, not conflicts of interest, but our time is up, but I'm going to just answer this briefly if I can. So I think they're orthogonal because it's just managing the blocks to be grouped together. In this case, there would be no actual data within the block, so I guess they'd be very small. So in a sense, because there's no actual data stored except for in the caching layer, and therefore the containers, I could hope, might accelerate it, but there would be benchmarking to be done.
I think it will even reinforce it. So this is simply a way to solve the many small files problem. You'll get more small files or more files into your name node. And so this exactly is also, there's a lot of files in the object store. So the only thing we present is storage steering and then a way for the data nodes to communicate with the provided store. If the name node does things more efficiently, we're super happy.
And with that said, our time is up. And thank you for listening.
So